Welcome to The Explainer. Today, we are going on a quest. We're going to try and build a perfect language. Not one with fancier words, but a language that has absolutely zero ambiguity, one that's mathematically precise. We're diving into the world of propositional logic.
You know, we've all seen this joke, right? A single tiny comma makes the difference between a family dinner and, well, something a lot more sinister. But what happens when the confusion isn't just a typo? What if the ambiguity is literally baked into the structure of our sentences?
Okay, take a look at this sentence. I saw the man with the telescope. So who has the telescope? Is it me or is it the man? Our everyday language, well, it just doesn't have a clear answer for us, does it? It's messy. And to escape this mess, mathematicians and philosophers started from scratch, designing a new language built on an absolutely unshakable foundation.
So if we're going to build this perfect language, we need the perfect building block. And in logic, that's called a proposition. It's a statement that has a crystal clear, non-negotiable truth value. 3 is an odd number. Yep, that's true. 27 is a prime number? Nope, that's false. There is zero room for interpretation. This is the atom of our new language. Okay, so we have our basic building blocks, our little atoms of truth. But that's just the start. To build anything meaningful, you have to connect them, right? And just like Lego bricks, propositions have very specific ways they're allowed to snap together. In logic, we call these connections the 5 logical connectives.
Let's start with the absolute easiest one, negation, or just not. It's represented by this little symbol here, not. So if we have a proposition, we'll just call it P, and P is true, well, then not P is false. And if P is false, not P is true. It literally just flips the switch. That's all it is. Simple.
All right, our first real tool for joining two propositions is conjunction, which you probably know as and. It uses this symbol, this. Now you gotta understand, this one's super strict. For any statement that's linked by an and to be true, both of its parts have to be true. And there's a perfect, simple rulebook for this.
And this table you're looking at, this is the entire instruction manual for the word and. There's no fine print, no exceptions. As you can see right there in that top row, only when P is true and Q is true is the whole thing true. Any other situation, it's false, period.
So let's see how this plays out. 3 is an odd number, that's a true proposition. 27 is a prime number, that's a false one. So we connect them with and. And because one of those parts is false, our rulebook, the truth table, tells us the entire statement is definitively false. Perfect clarity, no arguments.
Okay, next up, we've got disjunction, or, with the symbol V. Now, this is kind of the more relaxed, easygoing cousin of and. It's a lot more forgiving. It doesn't need both parts to be true, it just needs at least one of them to be true. And if you look at its truth table, you'll see it's almost the exact opposite of ands. Just look. As long as there is a single T anywhere in those first 2 columns, the result is T. The only possible way for an or statement to be false is that very last row, when both of the propositions you start with are false.
Now for a really interesting one, maybe the one that trips people up the most. It's called implication, but we know it as if-then. It's symbolized by this arrow. This connective is basically making a promise. It says, if P is true, then I promise you Q will also be true. And the only way this whole statement can be false is if that promise is broken.
Okay, I want you to look really closely at that second row. A true premise leads to a false conclusion. That is a broken promise. That's the only time this is false. Now, those last 2 rows can seem a little weird, but think of it this way. If the starting condition is false to begin with, the promise was never even put to the test, so you can't say the promise was broken. A false premise can imply absolutely anything.
And that brings us to our final connective, and this one is the heavyweight champion, by implication, or if and only if, with this double arrow. Come, this isn't just a one-way promise like the last one. Oh no, this is a statement of total logical equivalence. It's saying that P and Q are basically interchangeable.
And the truth table just proves it. It's as clear as day. The statement is only true in 2 cases. That top row where they're both true, and the bottom row where they're both false. For by implication to be true, the 2 sides have to match perfectly.
Okay, so let's take a step back. We've got our atoms, the propositions. We've got our glue, the connectives. Now, it's time to build something cool. By chaining all these things together, we can create what are called compound propositions, expressing really complex ideas, but with none of the messiness we started with.
Now, I know a statement like this looks super intimidating at first glance, but trust me, it's just a little puzzle and we have all the rules. Let's solve it together. First, we tackle the stuff in the parentheses. P or Q becomes true or true, and we know that's true. Easy. Next, the negation. Not R becomes not false, which our wheel says is true. Finally, we're left with the big implication in the middle. True implies true, and we know from our table that's true. The final answer is definitive.
And all of this leads to a really mind-bending question. We've seen that the final truth of one of these big statements depends on the truth of its little parts. But what if we could build a statement that is always true? Not because of the values we plug in, but just because of its shape. A statement that is true by its very design.
Well, the answer is a resounding yes, and these beautiful creations have a name: tautologies. This is it. This is the pinnacle of our quest. A tautology is a statement that is structurally perfect. No matter what you plug into it, true, false, whatever, the final result will always come out as true. It's a perfect logical truth.
And this, right here, is the proof. It's the evidence. We're testing if P then Q is really the same thing as not P or Q. So we work it out step by step for every single possibility. And just look at that final column. It's all T's, all of them. This statement's truth is just baked right into its structure. We've actually proven it.
And you know, for every superhero, there's a supervillain. The polar opposite of a tautology is a contradiction. This is a statement that is structurally flawed. It's doomed to always be false. The easiest example is P and not P. It's like saying it is raining and it is not raining at the exact same time. It's impossible, right? It's just logically broken.
So you might be thinking, okay, this is a cool mental puzzle, but why does any of this matter? Well, it matters a lot. This system, this perfect language, it's the fundamental language of every single computer on the planet. When you go to a search engine and type cats and dogs, the computer isn't understanding English. It's using the exact, strict, logical rule for and that we just looked at to filter the entire internet. This is the bedrock of our digital world.
We started this whole journey by looking at how messy and ambiguous our own language is, and we ended by building a system of perfect mathematical clarity. So I'll leave you with this question. Now that you know the rules of perfect logic, where in your own world, in the news, in conversations with friends, in arguments online, do you see its absence the most?